Hi everyone, and welcome to or welcome back to the Regression and Beyond series. In this lab, I'm going to be turning to generalized linear models. Specifically, we're going to be focusing on models that you might use when you have a categorical dependent variable. So that could be dichotomous, like a 0 and 1. It could be what we call a nominal, so just categories or unordered categories, or you can have ordered categories, what we might call an ordinal. The script file and data that I'll be using today are linked below, and then let's get started. So as with basically all these labs, starting with importing the data, again, using the Rio package. If you do it this way, just make sure, again, to specify the file location and name specific to your computer. So we have three independent variables, x1, x2, x3, appear to be continuous variables. And then we have two dependent variables, y1 and y2. Y1 is dichotomous, two categories that I've already coded as 0 and 1, and Y2 is categorical with three categories that I've coded as 0, 1, or 2. For the purposes of this lab, that Y2 variable we're going to treat as ordered and unordered. So generally, there's kind of two key parts of generalized linear models, including the specific ones we're going to be running through today. The first kind of key part is what we call the linking function. Two common ones, then the main one we're going to focus on is the logit linking function. But basically, the key idea here is it allows us to kind of retain that linear interpretation that is really nice with linear regression, right? The interpretation like 1 unit increase in this thing results in a 0.5 increase in this other thing, right? It's very easy to understand. The linking function is going to allow us to generally kind of retain that quality. So for example, we can describe kind of a linear relationship between an independent variable and the probability that a dependent variable's value is 1. Now, the other key part is the distribution. When you estimate like a traditional linear regression model with ordinary least squares, one of the basic assumptions is that the residuals are normally distributed. Now we're talking about categorical dependent variables, and we're not going to have that same assumption anymore. We still are going to make an assumption, it's just a different distribution. So for example, with a binary outcome, we're going to be using a binomial distribution. Without getting too much into the weeds, a binomial distribution describes basically the rate of successes across a bunch of trials. So if you have like a binary outcome, like something happened or it didn't happen for each particular case, a binomial distribution can be appropriate for that, right? Because for each case, there's a probability of being 1 or 0. And then we have a set of cases. So for this first part, we're going to start with Y1 that is binary or dichotomous. Now, to return to that linking function, there's two main ones that people tend to use, logit or probit. I'm primarily going to focus on logit, but I'll also show you a little bit about how you would implement probit. So starting with the logit linking function. So here's what we call, or might otherwise call, a binary logistic regression model. You'll see here at the beginning, now we're saying GLM rather than LM when we are doing linear regression. But otherwise, things look pretty similar here, and then we have some new parts. So this is where we are specifying the distribution as well as that link function. So you'll see family equals binomial, and then link equals the logit. So let's run that and see what we get. So this is our output. Generally looks, again, pretty similar if you ran a linear regression model as we've done in the previous labs. It's kind of more at the bottom here where things are a little bit different. We're seeing these terms like null deviance and residual deviance, and you don't see an R squared anymore. But we still get these coefficient standard errors and p-values. In this case, when you're using the logit linking function, you'd interpret the coefficients in terms of log odds. It's generally more common, though, to, or I would say probably to report both, but to report what are called odds ratios, which can be a little bit more intuitive to interpret. So I'm going to use the JTools package for this. I'm just going to load that real quick. And now I'm going to return to some of the spot model fit information I'll be talking about. But for now, you'll see that one, we get a generally kind of a nicer output that's a little more easy to look at and understand. And then right here is where we get those odds ratios. Now I kind of skipped it over right here. It says e to the power of the coefficient is equal to the raw odds ratio. Now with the logit function, a big part of it is the natural log. So this is why we're introducing, again, that e. E is kind of one of these things like pi, when it's just a number that exists and that's how it works. Or something like that. I actually don't know fully. So we can actually calculate these yourself as well. You know, it's really nice to do with a package like this and get a nice output, which we can also use without odds ratios to get that nice output. But we can also get the odds ratios ourself by exponentiating or taking e to the power of those coefficients. And that's how we're going to get an odds ratio. And in terms of interpretation, as one example for this x1, the odds ratio is 0.75. That would mean that with a 1 unit increase in x1, that would be associated with a 25% decrease in the odds of the dependent variable being equal to 1. So that was logit. Real quickly to show you probit. Again, nothing dramatically different. You see we're just changing the link function. Now notably, because you changed that link function, you are going to have some slight differences. As I note here, generally speaking, I would say I tend to see logit. That tends to be a bit more common. And if you're watching this and going to be applying these techniques, it's likely that you're going to be using logit as well. It's not, you know, inherently like mathematically superior in some way. It's just, at least in my experience, I tend to see logit more than probit. And when you're using probit, you're not going to exponentiate and get odds ratios that are often a little bit more straightforward to interpret, which is maybe one reason that the logit tends to be used more often. But I see probit popping up in a few areas. I think it sometimes can be topic or even discipline specific. For example, I've seen probit as a default linking function in some latent variable modeling approaches, which I'll be getting into in kind of a few labs down the line. But I want to jump back to our binomial model where we use that logit linking function and talk about this model fit information. First, you'll see we get this pseudo R squared. Generally, in my view, often reported, but honestly, they're not super meaningful. And if anything, I think they're a little bit misleading because they imply, that they're similar in some way to R squared, but you can't really interpret them like an R squared. So I want to focus more so on this chi-square value up here. Now, if you've watched the previous video, you might remember that we got a chi-square value like this when we were doing path models estimated using maximum likelihood estimation and then testing the fit of that model. So in that case, that was a likelihood ratio test, and we were comparing observed data with the model implied data. So that was one overall test, a test of exact fit. We also did chi-square difference tests. So when comparing different, what we'd call nested models. Now, generalized linear models are also estimated using maximum likelihood estimation. It's technically a different version of it, but conceptually, many of the things we're going to be doing here are going to be similar to what we have done before. So this default test that is reported right here is testing our hypothesized model, or this model that has x1, x2, and x3 in it, against what is often called a null model, or intercept or intercepts only model. It's basically the simplest possible model. It would just be saying that the dependent variable basically predicts itself. It wouldn't be specific, or in this case, for example, the baseline is the best predictor, could be a way of thinking about it, not any of these other predictors. But generally, right, we're getting this model because we think it's better than just the intercept or just the dependent variable alone. We think these independent variables are going to be helpful and explain or predict the dependent variable. So this chi-square statistic is testing our model against that intercept only model. And in this case, we would want it to be statistically significant because that would indicate that our hypothesized model is a better fit to the data relative to that intercept only model. You can't say it's an exact fit, but it's a better fit than that null intercept only model. Now, just to show you here, you can calculate it yourself. Remember, I briefly mentioned those deviance terms that popped up there. So the difference in those terms and then the difference in degrees of freedom, and you'll see now we get something that matches, right? 64.71, 64.71 with 3 degrees of freedom. So this would generally be a good thing. Our hypothesized model is better than our intercept only model. Now, at least with a binary outcome, it's relatively common to try to get something that is similar to what we did with that path model, or a test of exact fit. Or in other words, that null hypothesis is that our model implied data is an exact fit to the data that we have observed. So this one is often called just a goodness of fit, the G, sometimes reported that way. And you'll need a new package, GLM toolbox. That'll be helpful, as the name implies, for generalized linear models. So after you install that, you're going to want to load it, and then we can run this test. I'm not going to get into the weeds of it, but again, basically what you want to see is a non-significant result or a high p-value generally, if you think your model is a good model, and usually you do. Now this statistic is a chi-square value, and then those are the degrees of freedom right there. Now, another thing that's quite common with dichotomous dependent variables in these types of models is to look at the area under the curve, or AUC. And this can be particularly relevant if you're really focused on prediction and or classification. So when we run this, the reason it's called area under the curve, because it's literally area under what's called this, or here in our receiver operating characteristic curve. So a whole bunch of tough words to say all together. And of course, acronyms that often pop up and can be a little bit confusing. But to break it down even more generally, what do we actually want to see for this value of AUC? Basically, you want it to be higher than 0.50 or 50%, and ideally much higher. Again, if your goal is having a really good classifier or predictive tool, right? If we wanted to predict, in the medical or clinical things, what's like mortality, right? What's the odds that someone's going to die or not, right? Pretty big, pretty important. If we could have something that could pretty accurately classify, that would be very useful. And we want to basically do better than the base rate. It's kind of similar, again, to what we just did of testing the intercept-only model versus our hypothesized model. This is basically conceptually the same version of that. We want to do better than the base rate. Right. So if there was anything, I have an example here of recidivism. If we could imagine that our dependent variables were recidivism, or people reoffending and committing more criminal acts or unethical behavior, this type of thing. So in our case, 53% of cases are equal to 1, or 53% of people recidivated in this hypothetical scenario that I'm running through. So we could, without doing anything at all, we could just say everyone's going to recidivate, right? And we would be correct 53% of the time. But a model of saying everyone's going to recidivate is not very useful, right? Ideally, we want something that's a little bit more useful, and that's why we're including these other variables, other things that we think can do predict beyond the base rate. So I mentioned that AUC generally want to be above 0.50. There's a few heuristics about what can be a really good one or not, but basically you want it to be much higher, ideally, than 0.5, and the higher the better, basically, is the short story there. Now, another thing that comes out here is the Gini coefficient. This is just a normalized version of the area under the curve. Specifically, I show you the formula right here. So it really doesn't tell you anything different, but it can help a little bit with interpretation, because then it has a range of -1 to 1, with 0 would be that kind of 0.50 or 50% mark, or correspond to that AUC value. So basically, you want to be closer to 1 is good, closer to -1 would be a bad classifier. Now, you really wouldn't want to do this, but just to kind of illustrate this point about kind of classification, I'm going to create another variable with just the predicted values from that model. And then I'm going to code everything that's more likely than not, or anything that would say, yeah, this is probably going to be a 1. I'm just coding that as a 1. Otherwise, it gets coded as a 0. And then I'm just going to do a little contingency table here with the predicted and observed. So if you look at this last row here, you'll see the 83 and the 181, and you'll see I have this, I'm doing some math up here. Why am I doing that math? Well, the 181 would be the cases that in our model we predicted would be most likely to be a value of 1, and they were. So we were right. And then over here, the 83, those are ones we predicted to be 1, and we were wrong. So this little calculation right here, it's basically the number we got right out of the total number. Again, it's not an exact match to the AUC, and you really wouldn't want to do what I did right here and kind of report that. You'd want to report the AUC. But I just want to kind of illustrate that's really kind of the core of this idea here. Now, real briefly, I kind of jumped over this whole sensitivity and specificity, but generally a little better way of saying that sensitivity is the true positive rate, and then the 1 minus specificity down here, I'm going to think about as the true negative rate. So that's what's being plotted here. And again, the area under the curve, basically we want it to be more or greater area, which would indicate that you have a pretty good predictor or classification model. And that's where I'm going to end this part of the video. And in the next part of the video, we're going to pick up right where we left off, but then we're going to be moving into categorical variables with more than 2 categories. So I hope to see you in the next part of the lab.